All right. So jumping straight into a specific field that Aquinas addresses when he's talking about knowledge formation, he gives us a definition of mathematics. He says it studies what exists in matter in motion, considered apart from matter in motion. This might be a little bit surprising to us who are familiar with mathematical topics that don't seem to have anything to do with what exists in the material world. But going back to his original claim, he says mathematical ideas come from characteristics of material reality, but in mathematics we consider these aspects of material reality without thinking of their material existence, using the imagination, memory, and intellect to separate those characteristics from matter and arrive at mathematical truths. So again, as I mentioned, this might not be obvious if you're thinking about something in set theories or statistics, but the mathematics he's addressing at the time was much more just like basic arithmetic and geometry. I'm not going to go into this a lot here because I don't have nearly enough time to address it, but one of my sort of core claims or core ideas is that as modern mathematicians or people who are interested in math, we can trace a historical thread from our current concepts in math all the way back to those things that we do sense in material reality, like extension and like numbers of things. So what I want to say today is about how the formation of mathematical knowledge via the imagination tells us, important things we should consider for when we're teaching new ideas in math and in applied math. I use the word mathematics throughout this presentation, but it should be considered as mathematical science, applied mathematics, etc. All right. So for Aquinas, the imagination functions like a bridge between our sensory experience of material reality and our conceptual or intellectual understanding of the mathematical features of material reality. I'm going to give an example here. A triangle. When I say that word, you imagine something. You might not have right off the top of your head what the definition of a triangle is, but your imagination is producing something, and it probably looks like this or maybe that. On further consideration, we can say what the conceptual truth is behind a triangle, which is a definition like three-sided and closed rectilinear figure. In medieval and ancient thinking, this is sort of how we get the original mathematical concepts, is from sensing the world, imagining, and then coming to a concept about them. What I want to suggest today is that further, there's a reciprocal cycle of knowledge formation that always involves the imagination in mathematics. So I'm going to give some examples where we'll start with the conceptual statement and then see how the imagination can sort of fill in what that statement is concerning. So here's the first one, again from ancient or classical mathematics. This Platonic solid has pentagonal faces. If you know your Platonic solids really well, you know that's a dodecahedron. It has 12 of them, right? So here's another conceptual statement. This function is its own derivative. And again, just from knowing something about functions and their derivatives, I can say, well, that's the f of x equals e to the x function, right? So again, the purpose of these three examples, starting with what we imagined and then had a concept of, or were able to express the concept of, also goes the other direction. All right. In more abstract fields of mathematical thinking, the imagination has to shift from physical images, like we've been showing so far, to symbolic constructs like algebraic expressions or characteristics of sets of statistical data. You can see how these things just get more abstract in that history of mathematical progression. But I want to say this, that instructors, even in these more abstract fields, these areas where the imagination has to focus more on a symbol, instructors can still help their students develop their internal imagery that goes with new concepts, using symbolic forms that are based on and have continuity with earlier mathematical ideas. So I'll give another example on the next slide. What this looks like to me is an emphasis on verbalization and visualization. So visual exercises and verbalization of abstract concepts allow students to connect these abstract ideas with more foundational concepts in mathematics and provide students with opportunities to ground their new concepts in an appropriate imaginative framework. So I've chosen another example that's very abstract. This is the example of an epsilon delta definition of a limit in calculus. So you can see what the text at the top of the image reads might be difficult to just look at. Unlike the definition of a triangle, you can just read it and sort of see what it means. In this case, it takes a lot of work just to know what the terms that go into that proposition are saying, right? What I'm trying to suggest here is that even the conceptual grasp of something like an epsilon delta definition is possible by giving as many examples as possible where the epsilon and the delta are visible in the example, and then also by using natural language as much as possible to describe exactly what these relationships are to both the diagram that's in front of students and also knowledge they have from the past. So for instance, in the case of calculus, right, you're not going to introduce something this abstract and technical looking until your students know what a function is, right? But if they know what a function is, and they know how functions behave in certain ways on a graph, then building on that, using this visualization and verbalization technique, I think you can get them to the purely conceptual understanding of that, the definition at the top of the image. All right, just a few more things here. Okay, so I want to say this, and I think this is true for Aquinas too. The aim of math education is to build up abstract thinking, like it is for conceptual understanding. The aim of math education is to build up abstract thinking about mathematical ideas as they become more complex and less directly connected to the features of material reality. But since our understanding of these ideas is always rooted in our ability to know via abstraction from material reality, this cycle of knowledge formation that I've been describing indicates the need for a constant reference to the imagination and back to earlier stages of understanding mathematical ideas. Thanks so much.